A pleasant greetings to all. Myself, Dr. Dakshana, Assistant Professor, Department of Physics from Sathyabama Institute of Science and Technology, deemed to be University, Chennai. So, in this session, we are going to discuss one of a very important physics experiment. As we know, as a part of our curriculum, we offer a course called as Physics for Information Science for the first year BE and BTech students, in which for the practical session we have around 8 different experiments. Among them, one of the experiment is called as torsional pendulum. I hope this video will be very helpful for the first year BE and BTech students. So, the name of an experiment is torsional pendulum. The aim of an experiment is to determine the moment of inertia of a disc by torsional oscillations and to calculate the rigidity modulus of the suspension wire. So, before going to our experiment, let us have a short discussion regarding some basic fundamentals which is closely related to this experiment. So, what is modulus? So, modulus is defined as a ratio of stress by strain, where stress is nothing but a force which is applied per unit area, and due to the stress applied, if an object undergoes any change in dimension, then it is called as strain. So, let us see certain examples. In modulus, there are 3 different categories: Young's modulus, bulk modulus and rigidity modulus. What is Young's modulus? The ratio of normal stress by longitudinal strain is called as Young's modulus. Let us imagine we have a rubber band. We are applying certain force to this rubber band. So, the rubber band gets stressed, which means the rubber band's length change from its original position and to the new position. Now, when you release the force, the rubber band comes back to its original position. This is called as strain. The change in the length of the rubber band from its original position to the new position is called as longitudinal strain. The force which you apply to pull the rubber band at its both extent is called as stress. So, when an object undergoes change in length, then it is called as Young's modulus. Coming to bulk modulus, let us imagine we have a balloon in our hand. We are applying certain force. Let us consider you are blowing a balloon. Okay, due to this air which you give to the balloon, the volume of a balloon expands. When you remove the air, the balloon contracts and it comes to this original volume. So, the change in volume of an object is called as volumetric strain. So, the bulk modulus is defined as the ratio of normal stress by volumetric strain. Here, the balloon undergoes the change in volume. Then coming to the modulus of rigidity or rigidity modulus. Here, it is defined as the ratio of tangential stress by shearing strain. So, let us consider you are applying certain force to this object. This object undergoes change in its angle, then it is called as shearing strain. The stress which you apply to an object will make the object to undergo any change in its angle, then it is called as a shearing strain. So, rigidity modulus can also be defined as the ratio of shearing stress by shearing strain or tangential stress by shearing strain. So, these are the various types of modulus. So, using torsional pendulum, we can measure the rigidity modulus of a given wire. So, this is a torsional pendulum. So, before going to our demonstration, let me show you what are the apparatus which are required for this torsional pendulum. We required a uniform metallic string wire to which the circular disc is attached at the middle portion, as you can see here. So, now what is torsional pendulum? What does the word torsional mean here? The word torsional is nothing but twisting of an object. So, when you apply certain force to the object and the object gets twisted, then it is called as torsional. So, we have a metallic string wire here and this wire is attached to a circular disc. Now, you are giving a couple to this circular disc. What do you mean by couple? A couple is nothing but two equal and opposite forces. When this circular disc experiences a couple, that circular disc undergo a rotation, which means oscillation. The wire is getting twisted. Due to the twisting of a wire, this circular disc undergoes a continuous oscillation. So, this kind of oscillation which is produced due to the twisting of wire is called as torsional oscillation, and the entire setup is called as torsional pendulum. We are going to perform this experiment in 3 different positions. Position A, where you will be twisting or rotating the circular disc without any masses. Okay, coming to the position B, you will be placing a symmetric mass on this circular disc and you will be rotating the circular disc. And coming to the position C, you will be placing the same symmetric masses on the circular disc but a distance which is very apart compared to the position B. Okay, so these are the three different positions in which we are going to demonstrate the torsional pendulum. Now let me take you to the demo video to show how does a torsional pendulum work. So as you can see here, this is an entire setup of a torsional pendulum. So the apparatus which is required is a metallic string and a circular disc, two symmetric masses here, and each carries a weight of 50 grams and a stopwatch to calculate the time period of oscillations. So, what is torsional oscillation? The twisting of an object which results in producing an oscillation is called as torsional oscillation. So, how to measure a torsional oscillation? So, initially hold the circular disc in this position. You are going to apply a couple, as a couple is nothing but two equal and opposite forces. You can apply couple either by this way, that is you are applying a force in both left hand direction and right hand direction, or else hold the circular disc in this position, give a small amount of force by holding the screw. So, in the both left hand side and right hand side. So, now the pendulum starts to produce a torsional oscillation due to the twisting of this wire. So, to measure a torsional oscillation, let us have a pen. So, you can see there are two knobs, right? So, let us assume this is a knob number A. The knob number A goes to a new position and come back to its same original position. See here, this is its initial position A, it goes to the new position and it comes back to its original position A. So, this is one successive torsional oscillation. Like this, you have to measure 10 successive torsional oscillation. When you find your pendulum is producing successive torsional oscillation, you can go for measuring its time period taken for this oscillation. So, in our experiment, we are going to measure the time taken for 10 successive oscillation. In order to measure the time period, we have a stopwatch here. So, let us see how start the stopwatch and start counting the torsional oscillation. So, it goes to the new position and come back to the original position. Now, one oscillation, again it comes back to the original position 2. Similarly, it goes to the new position, again come back to the original position 3. Like that you can count for 10 oscillation, keep the stopwatch on so that you can measure 10 successive oscillation. Once the 10 oscillations are over, you can stop with the stopwatch and you can see the time period taken for to complete this 10 successive oscillation. This is our trial 1. Now stop the disc, again repeat this experiment for trial 2 time period. So now again give a certain amount of force for this disc. Now again the disc starts to produce torsional oscillations. Have a pen, see the position, this knob goes to the new position, again come back to its original position. So new position, again it comes back to its original position. This is torsional oscillation. Now again start the stopwatch. See what is the time required to complete 10 oscillation. So, the time period taken now to complete 10 oscillation will be our trial 2 measurement. So, that is our position A. Now, we are going for position B measurements. In position B, we will be placing these two symmetric masses at a very close distance which is very near to the center screw. So, make sure the masses are placed at equal distance. Using a scale, you can measure the distance between the screw and the masses. Let us assume the distance between the center of the mass and the screw is 2.5 centimeter. Now, again give a certain force to the circular disc, a couple which makes the wire to twist and the torsional oscillations are produced. Again count for the 10 oscillations by placing the masses close to each other. Let us see, this is the position A. Now after placing it goes to the position B, again come back to the position A. So now start the stopwatch, see the time taken to complete 10 oscillation, start counting the number of oscillation like 1, 2, 3 till 10. So once 10 oscillations are over, stop the stopwatch and note down the time taken to complete 10 successive oscillation. This is our trial 1. So now we are going for trial 2. Stop the circular disc, give a certain amount of couple, again the disc starts to rotate and produce torsional oscillation. So repeat the same experiment, note down the time taken to complete 10 successive oscillation. This is our part B position. Now we are going for the part C position where you will be placing the masses at the edge of the disc. in this way. So now you have placed the masses at the edge of the disc. Initially you have placed the masses which is very close to the screw. Now you are placing the mass at the edge of this disc. Now measure the distance between the mass and the screw. Let us say it is 5 centimeter. Now start rotating or start giving some couple for this circular disc. Okay, in a very small amount of couple is required to obtain a successive torsional oscillation like this. So now you can see it moves from an initial position to a new position. Again this mass come back to its initial position. So in this position C also we can produce a torsional pendulum. Again start your stopwatch, see the time taken to complete 10 successive oscillations. Note down the time period for 10 oscillations. So this is our trial one. Stop the circular disc after the 10 oscillation, repeat the same experiment and note down the time taken to complete the rest of the 10 oscillation, which will be your trial 2. So note down the time period for the trial 1 and trial 2 in all 3 positions. Make sure you are maintaining a uniform length of the suspension wire throughout all 3 positions. Okay, that is how you need to measure a torsional oscillation in 3 different positions. So as we saw in the demo video, how does a torsional pendulum work? It works in 3 different positions. So let us consider the position A without mass and the position B where the masses are placed at the closed distance as we saw in the demonstration video. So let us consider the position C where we have placed the masses at a different distance, which means the farthest distance D2. Now what we have done in the experiment is we have calculated the time period for successive 10 torsional oscillation. Let us consider the trial 1. Here I have given certain examples for the time period. Let us consider the time period for 10 oscillation which has been taken during the position 1 without masses. Let us consider it is 38 seconds in trial 1 and for the trial 2 it took 39 seconds to complete successive 10 torsional oscillation. What do you mean by mean time taken for 10 oscillation? Which is nothing but add the trial 1 and trial 2 and divided by 2. That is our mean oscillation for 10 successive torsional oscillation. Coming to the time period, here we are calculating the time period required to complete one successive torsional oscillation. Whereas here we have calculated the mean for 10 successive torsional oscillations. So in order to obtain one successive torsional oscillation, divide this mean value by 10. So the resultant answer is 3.85, which means the time period taken to complete one successive torsional oscillation. So the time taken is 3.85 seconds. Similarly, in a position B where the masses are placed at a closest distance, in trial 1 the time period for the oscillation is 42, in trial 2 it is 43 and the mean time taken for 10 oscillations is 42.5 and the time taken for one successive oscillation is 4.25 seconds. So the time taken for the 10 successive oscillations in the trial 1 is 44 and in trial 2 it is 45 and the mean time taken for the 10 successive oscillations is 44.5. And the time taken for one complete oscillation, dividing this mean value by 10, we get 4.45 seconds. So the length of the suspension wire at all the positions should be maintained constant. For example, during the demo video, I have maintained the length of the suspension wire at 55 centimeter. So this is our tabulation 1 where we have calculated the time period of the torsional oscillation at 3 different positions. Now we are about to measure the radius of this suspension wire. The reason is only unless or until you know the radius of a suspension wire, you can calculate the rigidity modulus of the suspension wire. So we are going to measure the radius of the suspension wire using an instrument called a screw gauge. So screw gauge is an instrument which is used to measure the radius of any object. The least count for the screw gauge instrument is 0.01 millimeter, whereas the least count is the minimum value this instrument can measure. As you can see here, the screw gauge has two scales. One is a pitch scale reading and another one is a head scale reading. So every instrument has its own error. Even screw gauge has its own error. The error in the screw gauge has been classified into 3 different types. The first one is zero error, positive error and negative error. As I said you, and also I am going to demonstrate you in the video where you can clearly see what is a pitch scale and a head scale. Now let us consider the 0 initially is our pitch scale 0 and the divisions here is our head scale 0. When the pitch scale 0 coincides exactly with the head scale 0, the error we got is a 0 error. Let us consider the second case where the pitch scale 0 coincides with the head scale division above the head scale 0. For example, if the pitch scale 0 coincides with 1, 2, 3, something like that in the head scale division, then the error is called as positive error. Let us consider the pitch scale 0 in this figure is coinciding with the number 2. Then the answer for the positive error, 0 error is plus 2. Let us go for the third case where you can have an error known as negative 0 error. So when the pitch scale 0 coincides with a division which is below the head scale 0, for example, you can see in this figure it coincides with the value 46, then this error is called as negative error. So these are the different types of errors which you can see in a screw gauge. So before measuring the radius of the suspension wire, make sure you are measuring the error of the screw gauge. So error plays a crucial role in determining the final answer of any object to which you are measuring the radius. So as you can see, this is a screw gauge. So using screw gauge we can measure the radius of the wire. So before going to the measurement, we are supposed to calculate the 0 error and 0 correction. So when you open a screw gauge, you can see there is a divisions inside this screw. As you can see now, this scale which you have here is called as a pitch scale. It has a divisions from 0 to 25, and the screw which you are rotating here also carries a division. It starts from 0 until 100 you have the division, and this is called your head scale. So the scale which is inside is called your pitch scale, and the scale which is in the topmost layer is called as a head scale reading. So before beginning the instrument measurements, we are supposed to calculate the errors of the screw gauge. So as I shown you in the PPT, the errors of 3 types: 0 error, positive error and negative error. When you are calculating the error, make sure the screw gauge is fully tightened. So the pitch scale, you can see only the 0 division inside your pitch scale. So now the pitch scale 0, if it coincides, for example, let me show you, if the pitch scale 0 coincides like this with your head scale 0, then the error is 0. Instead, if your pitch scale 0 coincides, as I shown you in the PPT, if the pitch scale 0 coincides like 10, this is called as positive error, and if it is like below the head scale 0, then it is negative error. Now in this instrument it is coinciding with 90, which means it carries a negative error of minus 10. So from 0, below the 0, it is getting coinciding at the 10th division, which is 90. So the value of the error is minus 10. So now we have calculated the error for this instrument. We can begin measuring the radius of the wire by keeping the screw gauge at 3 different positions. Once you have found out what is the 0 error and 0 correction, now we are going to measure the radius of the wire. So to measure the radius of the wire, open a screw gauge using the screw given. Now we are about to place this wire between the 2 knobs in the screw gauge. So after placing in between the wires, you can hear a tick sound, or you can give a good tight by placing the wire between the 2 knobs. Now we are going to measure the pitch scale reading and head scale coincidence. As you can see, the pitch scale reading marks the value for 0. There is no other division in this pitch scale reading. Whereas the head scale reading, you can see the 0 coincides with somewhere in the division in the head scale. This head scale reading has a value from 0 to 100. So the pitch scale 0 coincides with the head scale division, and this is called as head scale coincidence. So our pitch scale value is 0 and the head scale value is 57. So now this is how you have to take the radius of a wire using screw gauge. So repeat the same thing by placing the screw gauge in 3 different positions and see what is the pitch scale reading and head scale coincidence. Initially I have placed the screw gauge here. Now I am placing the screw gauge in this position and see what is the pitch scale reading. Now the pitch scale reading is again 0 and the head scale coincidence changes a little bit. Now remove the screw gauge, keep it in some other position and see what is the pitch scale and head scale reading. By taking down the pitch scale and head scale reading and in tabulating, you will be getting the radius of this metallic wire, which I will be showing you in the PPT. As I shown in the demo video, we have seen how to measure the pitch scale reading and head scale coincidence. This table is used to find the radius of the wire using screw gauge. So let us go for the zero error first. So let us assume our screw gauge shows a negative error of minus 15. Then what about zero correction? So if the error is negative, change the correction as positive. So here it is minus 15, when it is coming for correction it is plus 15. So for example, if here error is positive like plus 3, then the correction will be minus 3. So zero correction has a formula, so change the sign of a zero error into least count of the instrument. So the least count of the instrument screw gauge is 0.01 millimeter. So plus 15 into 0.01 millimeter is nothing but 0.15. So this is our zero correction. So coming for the pitch scale reading, as we seen in the demo video, the pitch scale reading was 0 and the head scale reading was 57, whereas the head scale reading is nothing but HSC into least count, which is our head scale coincidence 57 into the least count 0.01. So the answer is 0.57. So the total reading is equal to PSR plus HSR plus zero correction, which is pitch scale reading plus head scale reading plus zero correction. That is 0 plus 0.57 plus 0.15, our answer is 0.72. Similarly, I have taken three different pitch scale reading and head scale coincidence as shown in the demo video. By taking the mean for the total reading, we are obtaining the answer as 0.7066 into 10 to the power of minus 3 meter, which is nothing but millimeter. So now we have obtained the diameter of the suspension wire. From the mean, divide by 2, we will be getting the radius, that is r is equal to 0.3533 into 10 power minus 3 meter. So this is a table which shows the radius of the wire is r is equal to 0.3533 10 to the power of minus 3 meter. So using the two tabulations, we have obtained the necessary values which are going to substitute in the formula. In order to obtain the moment of inertia of a circular disc, the formula is I is equal to 2m d2 square minus d1 square t0 square divided by t2 square minus t1 square kg meter square. Now here the mass m stands for the two symmetric masses which we have used during the demo video. Here the d2 square is the farthest distance where the masses are placed. Let us assume it is 5 centimeter. And the d1 square is nothing but the masses when it is placed at the closed distance. Let us consider 2.5 centimeter. And t0 square is the time period taken for the first oscillation without any masses, and t2 square is a time period of oscillation which has been taken when the masses are placed at the farthest distance, and t1 square is a time period of oscillations which has been taken when the masses are placed at the closed distance. By substituting all these values, we will be obtaining the moment of inertia of the circular disc. So coming to rigidity modulus, the formula is eta is equal to 8 pi IL divided by r power 4 T0 square Newton per meter square. So where the Newton is nothing but the unit of force. Since strain does not have any unit, we are taking the unit of stress alone, that is Newton per meter square, the force applied per meter square. So here 8 into pi value 3.14 into the moment of inertia, the resultant answer which we will be getting from this formula, you are supposed to substitute here, and the L stands for the length of the suspension wire. As I said before, let us consider it as 55 centimeter, and R is nothing but the radius of the suspension wire which we have calculated using screw gauge, and T0 square is a time period taken for the oscillations without placing any masses on the circular disc. So as I said you before, where m stands for the symmetric masses, m is equal to 50 into 10 power minus 3, where d1 stands for the closest distance, that is 2.5 centimeter, and d2 stands for the farthest distance, that is 5 centimeter, and t0 is the time period for one oscillation which is 3.85 seconds, and t1 is the time period for again one period of oscillation with masses at the closest distance. The answer is 4.25 seconds, and T2 is a time period of one oscillations when the masses are placed at the farthest distance. The answer is 4.45 seconds. So by substituting all these required values in the formula, we get the moment of inertia value as 1.0631 into 10 to the power of minus 3 kg meter square. So coming for the rigidity modulus, now we have obtained the value for moment of inertia I. Substitute the value of I in the rigidity modulus formula, and all the values like L is equal to 55 centimeter are the value which we have got using screw gauge tabulation. So substitute all the required values here, and the rigidity modulus eta which we have obtained after the substitution is 6.3057 into 10 to the power of 10 Newton per meter square. So this is a calculation to obtain the value of moment of inertia and the rigidity modulus of the suspension wire. So coming for the result should be written as the moment of inertia of the disc, the corresponding value 1.0631 in 10 to the power of minus 3 kilogram meter square, and the rigidity modulus of the wire is 6.3057 into 10 to the power of 10 Newton per meter square. I hope in this session you have learned how does a torsional pendulum works and what are the various parameters you can measure using a torsional pendulum. So thanks for your quality time. See you in another interesting video. Thank you.